Yeah, I'm going to talk about entanglement-enhanced learning of quantum processes at scale. Oh, okay. So we want to learn about quantum processes. One of the reasons is that we can then use that information to suppress noise, to mitigate it, or correct the errors in devices. However, describing quantum dynamics is complicated. For an n-qubit system, you need exponentially many parameters, exponentially in n, to describe the dynamics. And to extract these parameters, you typically have to measure incompatible observables because things don't commute. It's quantum mechanical. And that means that we need exponentially many measurements to fully learn a process. However, this complexity, it also provides an opportunity for us to explore learning as a candidate for a quantum advantage. And in these tasks, the question is, can we enhance learning properties of quantum systems using quantum resources? For example, quantum entanglement. And the efficiency criteria here is the sample complexity. How many copies of the process we need to learn the process, the land. And so this has been explored recently. We had a great talk by Sitan early in the morning. And there are many theoretical results showing that, okay, with an ideal system, with ideal quantum memory, with ideal auxiliary systems, we can get advantage. And there has been actual demonstrations in this nice paper by Robert Huang and Google Group, and showing some proof of principle work in experiments. But yeah, the main question is, okay, right now, can we observe these advantages when we have imperfect quantum resources? Okay. And so here we want to show that, yes, with error mitigation, we can get entanglement advantage with noisy auxiliary quantum memory. And the problem is that, okay, we have some physical system that we are trying to learn its properties, and we have a quantum memory, but that quantum memory is noisy. So we have this quantum memory, and we can use it to probe another system. And if it's impacted by noise, we have to do something about it. And what we do is that we learn that noise, and we use it to mitigate it and extract the unbiased values. Okay. So the problem that we are looking at specifically is learning quantum channels. So we are given n copies of a multi-qubit quantum channel. Imagine you have a chip that repeatedly generates a process, some dynamics. And we are interested in the sample complexity of learning properties of this quantum channel, how many copies we need. And we are comparing two strategies. The first one is entanglement-free learning. This is the case where we have the system, we can probe the system, we can prepare entangled initial states, we can make entangled measurements. We can do things adaptively, but we are not allowed to bring in an auxiliary system and entangle it with our system. And on the other side, we have entanglement-enhanced learning. Those protocols are the ones that we are allowed to entangle our system with auxiliary memory, and then perform entangled measurements on system and some ancillaries, and other ancillary systems jointly. Okay, so these are the two types of protocols we're looking at, and and then we want to focus on the specific kinds of channels, and those are Pauli channels. So just to give you an example, for example, a 1-qubit Pauli channel, it's a mixture of all the Pauli operators, a probabilistic mixture. And you have a probability that you can apply identity X, Y, or Z. And another way to describe a channel is by its ion values and ion operators. So these Pauli channels, they are special because if you apply them to Pauli operators, you get the same Pauli operators with some ion value, lambda, which is also called the Pauli fidelity. And these ion values, lambdas and probabilities, they're all they are connected by a simple linear transformation. But the nice thing about the ion values is that they have a nice geometric picture. Basically, if you have block sphere, these ion values, these poly ion values tell you how much you're shrinking in a particular, this scaling factor in a particular direction. So for example, if we look at familiar noise channels, the bit flip channel is probabilistic application of the X gate, like a bit flip. And if you look at what it does to the blogosphere, it just shrinks the directions that do not commute with X. So those lambdas will tell you that, okay, lambda X here is 1, but the other two are smaller than 1. And you can look at the phase flip channel, it's the same thing, but rotated. So Z doesn't get affected, but X and Y do. So this is a nice picture to have, and it's also the way that we can extract information about poly channels in experiments. These ion values are the quantities that are accessible in experiments. So yeah, basically we put in a poly, we get a lambda, and we get the same poly, and we get this lambda ion value that we can measure and learn properties of the channel. And this was for a single qubit, but we can go extend it, generalize it to multiple qubits, and it's the same thing. Basically, we have a mixture of 4 to the n polys, and there are these probabilities or equivalency. We have ion values, and they're related by something known as Walsh-Hadamard transform. It's a Fourier transform over C2. But then the reason we are focusing on these poly channels is that they have many applications in benchmarking, error mitigation, and error correction. And they're also relevant for experiments. Any channel that we have, we can turn it into a poly channel by something known as poly twirling, which is essentially applying random poly gates before and after the channel. So these are relevant, and it's not just a simplification. This is something we can actually do. So yeah, so these are very nice and easy to work with, and they're relevant, and they have practical applications. And then, as I mentioned, learning them is just learning all these ion values. It's because they are the poly channels, they are diagonal in the poly basis. We just need to learn all these ion values, lambdas, and then that gives us the full description of the channel. And so what we have here is an exponential advantage in learning poly channels. So this is all in the ideal scenario where you have perfect ancillas. And in that case, you can show that there exists a protocol that uses n additional qubits, n ancillas. And then we can learn all the poly ion values up to some additive precision with using copies only linearly in the number of qubits. On the other hand, there is the entanglement-free version. If you don't use the ancillas, that is going to take exponentially many measurements to complete the same task. Okay, so this is nice. There's an exponential separation in the ideal case. And yeah, let me just tell you how it works before telling you what happens if. Okay, so the way that this protocol works is very simple. You prepare for each of the system qubits. We entangle them, create a Bell state with an auxiliary qubit. And then we apply the channel to the system qubits, lambda, and then measure them in the Bell basis. Using this result, and then we can repeat this process multiple times to get enough samples for better precision. And then by processing these results, we essentially get an estimator for all of the poly fidelities of the channel. There is a simpler way to look at this. Basically, when we do this, when we create these Bell pairs and apply the channel, we are creating the choice state of the channel. And the choice state of a poly channel has a very nice property. As you can see, it's a sum over lambdas and then tensor product of the same polys. And as we saw also in the morning talk, P tensor P and Q tensor Q, or PK tensor PK, or K and K prime, they always commute. So even though the polys individually don't commute, their tensor products do.
I wanted to, oh, careful.
What's happening? I don't know. I need to be careful about it. This has been done very carefully. So yes, and because this like we have some object that is a sum over all commuting observables, it means that we can measure all of them simultaneously. So by like extending this space, going to this larger Hilbert space, we have a bunch of commuting observables, and they can be all measured simultaneously, and so we get this advantage. Okay, so this is again very nice, and yeah. So in the ideal case, coherent access to perfect auxiliary qubits improve the complexity of learning. However, in realistic systems, quantum memory is impacted by noise. And it is not clear if this advantage persists in the presence of practical imperfections. Yeah, so this is what it looks like in real world, right? You have a circuit, the top is your system, bottom is the auxiliary qubits. You have to prepare all these entangled states, and then these are idling, they're impacted by noise, and it's not clear what's going to happen. So let me just go through these challenges. One of them is, yes, auxiliary qubits can be impacted by noise. There's also state preparation and measurement errors. Those will also impact our like the accuracy of the results. And also, we may not have qubits laying around to just entangle with the system qubits. So there is this issue of routing and adding just more noise to the already imperfect protocol. So this is where this new protocol comes in, this error-mitigated entanglement-enhanced learning. And the idea is that we perform the original protocol. We just prepare these bell pairs, apply the channel, and then measure in the bell basis. But then if the noise on the ancillary qubits are not correlated with the system, if they're in the tensor product form, we can realize that we are essentially measuring the product of these two channels because of the symmetry of these bell pairs. So we know what we are measuring. It's like just the product of the two, and they're diagonal, so it's very simple. So what we can do is to measure lambda prime, the noise on the auxiliary system, using some entanglement-free protocol, and then just divide the results. So this will give us the correct results. But the catch is that it might appear that we replaced the original problem with another problem of the same complexity because the ancilla is of the same size as the system. However, because it's idling, we can do things. We can apply additional twirling and some other techniques to simplify the noise, to tailor it to something that is not as complicated as the system noise. When I show the experiments, I think it becomes clear. But essentially, what I want to tell you is that this is not like some cheating. Ancilla is kind of different. It is an idling memory. So we have more control, and we can simplify the noise on the ancilla and like apply this protocol. OK. So let me first show you these results. How am I doing the time? Oh, 1 minute. OK. So so we don't, basically in the experiment, we don't have black box access to these poly noise channels. So we have to, we have gates, and we have to isolate the noise from the gate. And that we can do that by applying these poly channels, poly gates to twirl it and apply the channel multiple times, apply the gate multiple times. And then from the decay of those fidelities, we can extract the fidelities of the channel. And then there can also be correlations between system and auxiliary noise. That tensor product assumption may not hold. But what we do here is we apply some advanced dynamical decoupling techniques to ensure that the system and auxiliary qubits are decoupled. And basically, by learning and mitigating this auxiliary noise, we can recover the correct Pauli fidelities. And what I'm showing here in this plot is that the blue crosses, the dark blue crosses, if they match the black circles, it means that the protocol is working correctly. And it does. And the black circles are essentially obtaining these fidelities using entanglement-free technique, but that's serving as a benchmark for us. But that requires more resources. The black circles, they need 9 measurement settings, but the blue one is just 2. But the number of measurement settings alone is not the full story. The number of samples is important. So, and then that's where we go to larger systems. And what we see here is that, okay, we go to 8 qubits, and now we have ancillas that are not directly connected to our system. It's more complicated. We have 4 to the 8 fidelities. Of course, we cannot measure all of them using the entanglement-free technique for benchmarking, so we just measure a subset of them. And let me just show you the results. Yeah, so basically, if you see here, the left plot, the entanglement-enhanced versus entanglement-free. And just focus on the dark blue ones. Those are when we apply the error mitigation. And when they fall on the 45-degree line, meaning that we are extracting the correct information. And the light blue ones are without error mitigation. And basically, when we apply error mitigation, it removes the bias and we recover the correct values. We can also look at the overhead for doing this entanglement-enhanced learning with error mitigation, because error mitigation is adding overhead. So as you can see, we no longer have an exponential advantage. The number, like the additional measurements we have to perform, scales exponentially with system size. But it's much smaller than 2 to the n overhead that we had. It's like 1.3 when we do the fit. And the typical experiments that we do for entanglement-free learning is these tensor product of polys. And those are actually 3 to the n, which is, in this experiment, we have something like 600x improvement over the standard technique. OK, so with that, let me go to my conclusion and outlook. And yeah, thank my co-authors. Yeah, thank you.
Thanks, Alireza. There's time for maybe a quick question here. Yeah.
Oh, thank you for a nice talk. I'm curious about I think maybe the sample complexity will be increased due to the noise of the channel. So,
Right.
Can you quantify the amount of noise and the relation between the amount of noise and the increasing sample complexity in theoretical science?
Yeah, that's a very good question. So what I showed, that 1.3, that is with noise. The reason that is increased is due to noise. Now you may ask, okay, because it should be constant, basically. It shouldn't be something exponential, but it's instead 1.3 to the n. And now you can ask, okay, why it's 1.3? And it's related to the the spam fidelity, like the fidelity of your Bell state preparation and measurement, and also the fidelity of idling ancillas. These will all, we have a formula in the paper that connects that overhead that you saw to these numbers that you can measure from your gate fidelities. And yeah.
Oh, thanks.